All right, good morning. Everybody a little sleepy? You guys been having exams starting this week, or how? Has it been a while already, or one last week? So ours is scheduled for a week from today. Currently, according to our syllabus, let me pull that over for you. We're on track to take care of membrane filtration today and next time, and that leaves us with a exam review time outside of lecture time. So I'll have you kind of fill out a little survey towards the end of class today to give your thoughts on that, about when you'd like that, what would be a good time for you to participate. So we'll talk about that in a little bit, but we'll go ahead and get started. So last time we talked about granular filtration, pretty much wrapped up what I wanted to talk about there in terms of really what do those problems look like. They're fairly straightforward so long as you kind of understand what you're trying to do, right, to account for how much water you need in different places. So today we're going to get into membrane filtration. You may have had or might take Dr. Kofi Christie's membrane class, so this is just going to be a kind of a rough overview compared to that, kind of the fundamental processes for, we might think about with regards to membranes. So last time when we were doing granular filtration, we said that sort of filtration through some bed of sand, and it's not exactly size exclusion. There's a lot of little processes going on, whereas our membranes are going to be some kind of a size exclusion process where we have some particles in our water that's flowing through a membrane, and then they get stuck and repelled. And a lot of times the way we'll do this is we'll operate it in a way where we can have a waste stream where all these particles that are getting stuck, they don't just sit there forever. There's a current flowing to the side that we can collect the concentrated solution of particles, and on the other side of the membrane we're getting the cleaner water. So we're going to talk about kind of the basic setups we might use and what those look like. So first, a definition of a membrane. Again, we did talk a bit about this, but usually what we're going to use them for is particle removal. If we get really fancy, maybe we'll get down to reverse osmosis to reject particular ionic species in water. But typically it'll be particles, and then we could go down a step and say, well, we've got these colloids, things like viruses, that are really practically dissolved, but they are physical. They're still physical particles, but they're so small they act kind of like they're dissolved. Then we can get down to chemicals, so literally just molecules, large molecules. Something like a pesticide that we want to get out of our water. Sometimes these will be larger molecules, and we can remove them with nanofiltration. So we would talk about different types of filtration in some way based on how they are, what size they are, what classification we're using. So if we're just doing particles, that would be a granular filter could do that pretty well. And when I say particles, probably on or near the scale of micrometers. We talked about viruses bacteria being about micrometer size, and we talked about sedimentation. So anything that was like close to being able to sediment, but maybe wouldn't quite, that's the kind of thing that we would do with a granular. Getting down below that, and I guess we could, a membrane version of a granular filter, or on the same size, we might call that microfiltration. Anything below that we would call ultrafiltration, or we're getting to the point where we can remove viruses, very small particles. Then down to the nanofiltration if we're talking about the chemicals. and ultimately reverse osmosis when we push that nanofiltration even smaller, and we're really causing some separation of the ions from solution. Now, the definition of a membrane itself from the dictionary here would be a thin, soft, pliable sheet or layer, and often referring to like some plant or animal origin. So there's a lot of biological materials that act as membranes. Another another way to describe it would be a piece of parchment forming part of a roll. So those are our definitions for a membrane, and we'll take a look at this the way that pieces of paper can kind of give you a good picture of that. Okay, so what about our history of membrane use? Well, really they've not been used for a huge amount of time in water treatment, especially in terms of being particularly common. They were first used 60 years ago or so, but really were not popularized until about 30 years ago. So relative to chlorine, that's been around over 100 years now, it's a little bit more recent, right? So the actual use of a membrane designed to remove stuff for water treatment is it's pretty recent. One thing to note, just overall, the pressure that we need to supply is usually the biggest cost outside of the actual infrastructure itself, making the membrane, designing it, and getting it taking care of it. And that pressure is going to be inversely proportional to the pore size. So if we need to remove really small stuff, we need really high pressure. So if we say size is very small, then our pressure and therefore energy costs are going up. And that's just going to happen. You may or may, how many of you have heard of graphene? It's like, a few years ago, it was like the wonder material for nanotechnology. Basically, graphene, it's a lot like graphite. It's a carbon material. And if you've ever played with graphite, you see it like, it's kind of flaky. It has like sheets. And essentially, these sheets are just repeated benzene rings. And you just have a bunch of these benzene rings in a row, making an entire flat sheet. And people were excited about graphene, like, hey, maybe we can have this perfect filtration system where one water molecule can make its way right through between these rings, and it would reject everything else. And it fits so perfect that there's, it'll be such a low energy, cost savings thing. But that's all baloney, because in order to have membranes operate, you are always going to have this pressure requirement, if for no other reason than osmotic pressure. So water doesn't want to go away from a salty environment. That salty environment is going to pull the water towards it. So there's always going to be osmotic pressure, and there's always going to be resistance to flow based on the space with which the molecules, the water, can flow. So that's all kind of silliness, the graphene stuff. Even though theoretically, we could get close to this ideal spot where we don't have any true, or we have minimal membrane resistance, there's still going to be a pressure requirement proportional to the size of our pores for the water to flow through. Okay, a couple of operational terms. We're going to describe the permeate. That means the stuff that kind of goes through, that permeates the membrane. That's our treated water, typically. Sometimes we're not interested in that. Maybe sometimes we're actually just harvesting whatever particle that we're filtering. And so sometimes we're actually more interested in the dirty water. Let's say we wanted in a lab to concentrate a culture of bacteria. We might use a filter to collect the bacteria in a smaller volume of water. So in that case, we don't really care about the permeate. So just depending on what we're looking at, this treated, that just means we've removed stuff out of it. So then we have the feed. That's pretty obvious. It's whatever we're applying to the membrane, and then we would expect that's going to be the dirty stuff that needs to be treated. Then we can have a third flow if we're operating in this continuous mode. I'll describe that a little more in a moment. That could take the extra concentrated stuff, so the feed meets the membrane rejects a lot of these particles or whatever we're removing, so we get a lot of them there. And so this flow would be taking those away from the membrane. So we'd have three separate flows: the feed flow coming to the membrane, the permeate going through the membrane, and then this concentrate flowing beside the membrane and away from the membrane. So if we were to draw that, say we have some membrane here, we'd have the feed, the permeate, and then we could imagine a concentrate could look like that. So we're going to look at a lot of diagrams, make more sense of this, and flesh this out more. The concentrate feed there, it's a little bit optional in some sense. This is a little bit like having a continuous flow system versus a batch flow system, because, or a batch system. Because if all we had was a feed and no concentrate, eventually this membrane is going to get so clogged up and fouled that it really makes no sense to keep trying to use it, because it's just clogged, right? So we may be able to do what we'd call dead end filtration, where we don't have any concentrate. We just filter a certain amount of water through and then stop. So we'll get into all that. All right, so here's the kind of the two diagrams. This continuous system would be a cross-flow filtration, where we have this feed, and this would be in the context of some pressurized chamber, by the way. So we apply pressure, so we don't let that retentate come out very easily. We pressurize this. That way, water wants to escape through the permeate channel, and we are balancing between letting some out the retentate here, or this concentrate. So those are the two words we can describe this. We're adding the feed. A lot of times we'll pressurize the feed itself. Sometimes we might apply a vacuum at the permeate. Either case can work just fine this way. So we could say pressure here often as a positive, or maybe a pressure here as a negative. Regardless, we will have some delta pressure. And we're going to define that essentially across the membrane. That delta P from in front of the membrane to behind the membrane is what's going to drive the water through, right? That's going to be what we would call the transmembrane pressure. All right, so that means that in this setup, it actually doesn't really matter how we draw the feed. We could draw it coming in here, kind of like I did a moment ago. It doesn't really matter where the water is coming from, so long as we have this dynamic where it's meeting the membrane and then can go away from the membrane. So this would be a system where we could operate continuously. Presumably this crossflow helps carry away these particles, and then we'll do some routine maintenance like backwashing, a lot like we did with the granular filtration. And then we might do some other techniques to wash it a little more rigorously. And for membranes, it's actually pretty common to just do a small, quick backwash on the order of 30 seconds or something every couple minutes if you've got like a dirty system. So you can do membrane operation in a bit of a different manner than granular filtration. All right, so then we can take a look at two diagrams then that would be sort of the box diagrams here. One would have a cross-flow system, and the other would be dead end.
You're probably most familiar with dead-end filtration in terms of syringe, like using a syringe filter in a lab, where you'd have some syringe and then you'd add this little filter device that attaches here. You push it through and you get filtered water coming out. That would be a dead-end filtration. So the way I'm going to draw this on this little box diagram is to say I'm going to add a little thing here that we will call our membrane. So if that's our membrane, then we really just have two flows here. One would be the feed and one would be the permeate. Now, we can retain some concentrate here. In a dead-end filtration like this, what we could do is say this is before, and then a little bit later, you know, and maybe we have some particles or whatever in there. A little bit later, we have this remaining amount of water, and presumably whatever was rejected, the particles or cells or something, then we've concentrated them, okay? So we'll look at an example problem of just that in a little while. So that could give us a way to concentrate a solution, but it's not a flow rate, right? We just have done it in a batch sort of a scenario. We've concentrated a little bit of it, it's just sitting there now, and we also produced a little bit of permeate, however much volume we pushed through that filter. Okay, so that's the deal for dead-end filtration. Most of what we'll talk about in terms of practical plant scale systems would be cross-flow filtration, so that we can better manage the membrane and have longer lifetimes there. So we'll say we'd have a feed here in a cross-flow system. And then what I've done here is I've drawn several arrows, 4 arrows, to highlight that we can draw this in a couple different ways. And based on the way we draw it, we would label the arrows. Because again, it doesn't really matter, like I said a moment ago, you know, if we were to draw that here, or if we were to draw the retentate like that, what matters is what's crossing the membrane. So if we draw the membrane in this little diagram, and it's pretty common to do it this way, if we draw it that way, we just have to look at what has crossed over that membrane in the system, right? So in this case, the stuff that did not cross is going out here. So that would be the retentate. We could draw it just as easily like this, and it would still be correct so long as we change our labeling, right? So I'm going to go back to the way I drew it first, in case you already started that way. So it doesn't really matter too much so long as we check, okay, this one does not make it through the membrane, so that's the retentate. And then we have a redundant line here because we see that both of these should be the same. So we could get rid of one if we wanted to, or get rid of this one, or just label them both. It doesn't really matter. These are the permeate. Because it's crossed past that membrane barrier that I drew up there. All right, so that's kind of the basics of how we would look at the membranes themselves, how we might draw them in a kind of a box diagram and look at it that way. And I was kind of ahead of myself here, so this is just a couple more examples to flesh that out. We've got these 2 different flow regimes: dead end, which acts like a batch. Whatever remaining solution there would act as a concentrate. So you see in this photo, maybe they've already pushed some water through and they stopped there. You could remove the filter at that point and put that somewhere, and you've collected a concentrate, right? So, and then of course the cross flow. All right, so we've covered that by now. Okay, a couple more examples of where you might see these in practice in a laboratory, just to kind of show you what it might look like.
You may see some glass device that looks like this, and it has a support material right here that you can add a membrane onto. And so if you add the membrane, kind of where I've drawn this red line, it's supported by this porous glass substrate thing, and then you would fill this with some water or solution that you want to filter. And then essentially what you would do is apply a vacuum here. And the water would flow through, and presumably it would be collected. You know, you could add in some beaker or something here and start filling that, and this would be your permeate. And this would be your feed. So the vacuum then is giving us the delta P. And one thing to note here is that for filtration, if you're going to use the vacuum, you have a hard pressure limit equal to atmospheric pressure wherever you are, right? So if you were applying this vacuum and you have a pump that was really, really effective and could get to a true vacuum pressure, so absolute zero, I suppose, then your pressure difference is equal to exactly what your atmospheric pressure is. So if you do this, if you have that pump and it works here, that's great. You take it to somewhere in Colorado, you know, pretty high up in the mountains or something, then you've got a lot smaller of a pressure suddenly. So it's actually something that you would may need to consider. And when we think about the different membranes that we might want to use, we could see that, hey, if we need this nanofiltration stuff, we probably have to pressurize the feed with pumping pressure into it rather than trying to pull it out and use the atmospheric pressure. So we can, you know, we would have some consideration there. So I'll just write a little note. So for vacuum cases, the delta P is always going to be less than or equal to the atmospheric pressure. Okay, so that's another device you might see in the lab, kind of a lab setting. For a cross-flow filtration, I want to highlight this one because it's would hopefully help us see how this cross-flow scenario could happen in practice and what that might look like. So this already has some labels, but I'll kind of walk you through it here. You know, again, we're talking about this type of system. In a little box diagram, we might draw it to look something like this, right? And then label all of those. But what does that actually look like in a real setting? Well, here in this scenario, I'm going to change color a little bit. In this scenario, we've got some feed here. And that's being taken. There's a pump, if you look back here, that's applying some pressure. So we've got our feed line coming to our membrane system in that direction. The membrane itself is housed right in here. So we've got a membrane inside there, and what it looks like to me is that it's some tubular membrane, and we'll talk about it, but we can have membranes in a lot of different forms. So this looks to me like it's a tubular membrane where water's coming into the inside of the tube, and we have this system pressurized. So this is likely some sort of a pressure valve letting some water through, but you require some pressure to do so. We see there's water coming out here with still some pressure there. This is going to be our retentate, or the concentrate. So water that passed across the membrane but didn't make it through the membrane. So it moved by the membrane. And the reason I know that is we can actually kind of see there's, if you look closely, I don't know, yeah, it looks like it's showing up there a little bit. You can actually see there's like kind of this clear plastic casing here. And inside that, the actual membrane here, you can see that. And then there's water that's collecting and draining through here, and that's our permeate as it's labeled. And you see very clearly that this water is looking a lot cleaner than the other water, right? If you look really close, maybe we could see, or we probably would see if we really took a careful comparison or were able to, that the water here is not as cloudy or as dirty as the water here, right? Because we've cleaned some of the water and taken that out, and that concentrates what's in there. So what's happening inside this membrane then, or this casing, is we have sort of two tubes, right? The outer casing, that's the clear plastic that we're looking through. Then the inner membrane itself, which is like a tubular membrane. Anything that, as the water is passing through here, it's pressurized and it tries to make its way through this membrane material because it's porous, and some of the water escapes. Any direction through this tube, it'll make it into the wider sleeve, and that wider sleeve drains right into this nozzle, right here. Does that make sense? Kind of get the picture a bit? So that's going to be one of these cross-flow systems in practice. And you can see now that this box diagram thing is just a very conceptualized way of showing it, right? That doesn't necessarily look, membranes don't actually look like they're arranged in that manner. That's just the flow diagram. Okay, so a few things to consider about designing membranes. One of the first things is going to be the contaminant size. Okay, what contaminant are we looking at? How big is it? That's going to inform what kind of a pore size we need for the membrane, pretty obvious. But then that gets to, well, what kind of pressure and flux do we need? So if we need a high flux, that might mean we need a lot of surface area. Certain membranes, if they have a small pore size, you're not going to get a very high flux through them. So there's a few things. It's not just the pressure, but there's also a kind of a production rate across the membrane. Just a quick comparison to sort of groundwater and soil stuff, thinking back on the granular filtration. If you've ever tried to pour water through clay, or to watch how quickly clay will take water, like a clay type soil, it turns out that it flows very, very slowly through it. In fact, we use that in a lot of our environmental engineering projects. If we want an impermeable layer, we get a nice clay, and it really acts as a water retardant. It just won't let it through. That's because there's very, very small pores in a tightly packed clay material, because the clay particles themselves are so small. We make this soil that is really, really tiny pore sizes. There's no way the water is going to flow through it very well. So maybe we'll get a very tiny amount. So tiny pore sizes, we get a tiny amount of water going through it, right? Whereas if you ever pour water onto sand, you'll notice, oh, it kind of just goes right through, right? It'll just travel almost immediately to a resting spot somewhere below it. All right, so then we have the operational pressure and operational flux. And typically we can do either constant pressure or constant flux with membrane operation. It turns out that normally people want a constant amount of water if we're using this for water treatment. And so while sometimes in a lab setting, maybe it's easier to do a constant pressure and see what happens, in real life, we will almost always be doing constant flux and adapting our pressure in order to make sure we're meeting that flux. So we can do constant pressure or constant flux. But since we expect our membranes to foul over time, there's going to be an increasing pressure requirement to achieve the same flux. And these two are going to be related. Just say this is typical for real applications, I'll say. Okay, and again, that flux is going to be whatever flow rate we achieve across that membrane, right? So just like the granular filters, we had some area of the filter itself, pouring some water through. We get kind of a velocity term in some sense, or we could look at that as a flow rate divided by some area. So it's the same principle there. We're going to elaborate a bit on it. But those are essentially the design parameters. Okay, what kind of membrane do we need? That's going to correspond to some pressure requirement, some production rate that the actual membrane can handle, or some flux that it can achieve. And how do we operate our pressure accordingly? Okay, so here's a table that kind of merges a little bit of what we looked at in terms of the particle sizes or contaminant sizes with typical operating processes, fluxes, and pressures. So we saw, when we were considering sedimentation, stuff that kind of looked like this, right? We saw, okay, we have sand we could get rid of, and when it says conventional media filtration up here, that's like our rapid sand filters or granular. So then that can cover several things. I mentioned microfiltration earlier as kind of equivalent or similar, and you see there's a bit of overlap here. So if we're looking at something that's on the scale, and this axis up here is in micrometers, looking at a 1 micrometer particle, that would be pretty similar to bacteria, right? That's sort of where our bacteria, algae, things like that are. And if we look, we find the clays. Here's these clay particles I mentioned are pretty small. And you can imagine the pore size of water trying to travel through a fine clay. That's going to be pretty small pores. All right, so given this about 1 micrometer, we might call that ultrafiltration down to 0.1 micrometers. So if you do go into a lab and use one of these syringe filters, and maybe it's a 0.45 or 0.22 micrometer, we might call that a microfiltration membrane. That's the syringe filters, right? That's the scale we would use for that. And those would do well if you wanted to remove some bacteria, if you just wanted to get any particulate matter, that clay and stuff out of a water sample. You didn't want to run that through your instrument, you run it through a syringe filter. There you go. Now we get below that and we get ultrafiltration. And actually I'm going to take a step back from there. Again, looking at the microfiltration and the conventional, the pressure requirement in kilopascals is really somewhere between 10 and at the most a 100 for there. And just as a kind of a reminder or a demonstration, the pressure units here, so kilopascals, about 7 kilopascals is 1 psi. Okay, and another way we could look at it is 1 meter of hydraulic head, water on top of a filter, is about 10 kilopascals. So if we have 10 kilopascals, that's talking about 1 meter of water stacked on top of something. So if you go swimming and you're a few feet under, you've got about that much pressure on you just from the water above you. So then to achieve microfiltration, if you're just going to use gravity, you probably could. If you just have about 10 times that,
so instead of 1 meter, you have 10 meters, then you're at a point where you can drive a membrane with just gravity-fed water. So this here, so if this is about 1 meter of hydraulic head, and then that would mean this is about 10 meters of water. There are actual pretty neat applications where you have it's called the sky hydrant. It's a membrane system designed for scenarios like disaster relief, or maybe kind of developing country scenarios, or situations where there's a need for water. All you can do is elevate it. Maybe you have a pump that can elevate your water for you, and then you can use that tank and supply the pressure required to do some ultrafiltration, which, around in this area should get us removal of most, if not all, viruses. So that's corresponding with a pore size of about 0.01 micrometers, so 10 nanometers. Most viruses are at around 20 nanometers or larger, in between 10 and 100. So that's pretty neat, because then that kind of gives you a sense of, oh, we can actually filter water effectively and get a lot of contaminant removal given that amount of pressure, right? About 35 feet or so in the air. That is a fairly, large pressure differential, but it's certainly something we could practically achieve. Now, the other thing you'll notice here is the hydraulic flux. So as we're increasing or decreasing the pore size, we're increasing the pressure required. We saw that, but it seems pretty manageable. But then if we look at the hydraulic flux, we don't have it all the way out here, but the microfiltration, a typical microfilter membrane would give us about 100 liters per square meter of the membrane area per hour. So in that sense, we can imagine, okay, we have 1 square meter of membrane, we give it 1 hour, we produce 100 liters. Okay. Then if we take that from a microfiltration system down to a nanofiltration system, that is now just 10 liters. We can go all the way down to a reverse osmosis membrane, and that's 1 liter for that hour. So the pressure is increasing and the flux is decreasing given the change in pore size. So we really see here why it gets expensive to do reverse osmosis to treat a fair amount of water. It's certainly possible. It is something we can do, but it gets, the smaller the pore size, the less we produce, and the higher pressure is required to produce it. So there's kind of a double issue there. So when it comes to water treatment generally, membranes are a good example of the how and the why we can treat pretty much any water that exists and get it to a point where it's totally fine, safe to drink. We certainly have that capability. So if you're ever hearing people outraged about, oh, we're going to run out of water, that's not actually true. It's just going to be a little more expensive to treat it, if anything. It's going to be a matter of, well, we have to pay the energy cost. So energy then, access to energy is extremely important if we care about access to water. All right, so let's talk a little bit about the type of material we can make membranes out of. There's really 2 classifications we would say. One would be polymeric, so out of some sort of polymer material. I think we talked a little bit about polymers already. Basically, we take some monomers, so individual molecules, and in a controlled manner, we cause them to polymerize. So one links to the next, which links to the next. There's usually certain types of molecules that can do this really well. We trigger that with some initiating system, depending on the type of molecule they are, how their chemistry works. And for example, we can get cellulose, which is sort of a plant-based polymer.
We get polyvinyl chloride, or PVC, polymethyl methacrylate, which is kind of your acrylic stuff. So that's PMMA. All sorts of others, right? There's a bunch of acronyms if you ever look into polymeric membranes. There are quite many. So there's plenty more than what I'm listing here. And the reason I'm listing a few here is just to show you that we can make them out of different stuff that could impart different properties to them. Maybe they are more or less hydrophobic, so they will do a better job handling certain types of particles given their kind of the surface chemistry on there. A lot of people have looked into, can we prevent them from fouling? Can we prevent them from allowing bacteria to grow on the surface and start munching on all the junk that we're filtering? Because sometimes that could even cause harm to the membrane itself. So there's a lot that goes into membrane design. Okay, how do we deal with these? How do we deal with the fouling? We'll talk about more, I think, next time. We'll get into the fouling a bit deeper. But all sorts of stuff that we can potentially do here. So the surface chemistry is one interesting component. And we might say that's stuff to do with charge, hydrophobicity or hydrophilicity. We could look at the fouling tendencies or potential, and also how easy is it to clean. So sometimes it's not just backwashing, we will do a chemical cleaning and add some, maybe bleach, maybe peroxide. We'll add something here, acid or base, to wash it, to really just try to get it back to the original state where it's very clean. And that's going to present a little bit of a problem if those cleaning agents attack the polymer itself, the membrane. And so for polymeric membranes, we typically are kind of limited. Sometimes we might also want to heat it to get stuff off. But again, plastics are not so happy to be bleached or heated or things like that, right? So that kind of leads us to the next type, which is a bit newer in terms of what's actually been used, and that would be ceramic membranes. So if you get a really highly controlled ceramic, you can create a membrane. If you think about it, if you've ever played with ceramics or even just drink from a ceramic mug or something, you'll know that, well, one thing, you can glaze them, and so that kind of seals off everything nicely. But if you look at an unglazed portion, maybe the underside of a mug or something, you can feel that it kind of feels porous. And if you designed it right, you could have a controlled porosity and actually be able to filter water through that. And so that's essentially what happens with these ceramic membranes. So they are brittle in the sense you try to get them really thin and porous, so you can imagine it would be very easy to snap them, right? It's this brittle ceramic material. But if you protect it from against that, maybe have a nice support layer, house it in a very nice system that's not going to allow any sort of bending or anything like that, then these membranes themselves can handle a lot of pressure. So a polymeric membrane, if we were to look at kind of what it would look like inside, it would probably look kind of spongy. In here there'd be pores, and if we apply too much pressure to some sort of a plasticky, rubbery material, you can imagine it could collapse, right? Now, if you do that to a brick compared to a styrofoam, a styrofoam brick compared to a ceramic brick, you can imagine just, mentally that image. Which one's going to compress first? Which one can handle more pressure? Well, the ceramic membrane would be able to handle a higher pressure for that transmembrane pressure. It also has the great advantages of being chemically resistant and heat resistant. Since it's kind of a mineral stuff, it's going to be pretty hard to degrade it unless you're really, really trying. So ceramic membranes, they're a bit more expensive to manufacture, but as that improves, and to the extent that we can have a nicely controlled application for them, they have some attractive benefits there. So they're finding a bit more and more use. It is hard to arrange them in the right way, or in high density ways like we can with the polymers, which we'll talk about right now. And I'm going to grab some paper to demonstrate this. So how do we actually assemble a membrane in a way that uses the properties well, the surface area well, and all of that? Here we see this spiral bound or spiral wound membrane. If you think about just one sheet of a membrane, we could just leave it like this and put it in some sort of housing and apply pressure across, you know, if this paper is a membrane, and get filtration from one side to the next. That would mean we'd probably need some sort of thickness here, so the plumbing, all the piping on either side of it. And so this one, you know, let's imagine this was 1 square meter, would occupy some larger volume. And so we'd need lots of cartridges or lots of units like this, and we'd have to stack all those. That would end up occupying a lot of space if you wanted to have lots of square meters, right, of membrane area. So we can actually do something pretty clever, and actually have a few pieces of paper here. So instead of operating them all, you know, each sheet individually, what we can do is we can arrange them with some sort of spacing between. And if we do that, if we space them between each one, then we can actually wind them, as we kind of see in that picture, around themselves. And even this would even work if we just had one of them. But now we have a system where we can actually plumb it, so we can pour water in one way, pressurize it. Any water that passes across one of these can then travel inside that spiral because we've added that spacing material. So we have, at no point can water just find the other side if we do it right. So water has to go through the membrane to find the other side. But we have a really high surface area because we were able to wind them in this manner and have these materials. You'll see it kind of right, if I can find my cursor. This material right here, that's the spacing material. And so if we do all the plumbing inside here correctly, we get a really high surface area for our membrane and in just one cartridge, right? And so it's really allows us to make a much more compact, more higher density, so to speak, situation for our membrane. So that's a great possibility, just winding the membranes. And that's an example of where the ceramic filters are going to have a disadvantage, because unless we perfectly crafted them into that form in the first place, which seems a little bit of a hard ask or difficult task, that's the polymer membranes are going to have a big advantage here. Okay, so then let's just take a quick look at what's actually happening here. So we see a permeate coming out here, and we see a permeate coming out here. We also see retentate coming out, and what's happening is, in our scenario with the spiral membrane, is as water meets it, some is passing through into the permeate. So we can just even think about just one membrane here. If you're giving water to it, and you're giving it to it from the outside of this cylinder, just like that one we looked at in the picture, water could pass through, and then it would be permeate. But anything that's remaining outside of here is going to be the retentate. And we might be feeding the water from this direction or something, right? Anywhere around it. It's coming, meeting the membrane, and then
leaving one way or the other. And so that's essentially what's happening. We see the feed is coming in to the middle in between the layers. So it's being driven on one side in between the layers, but not like inside the core. So if it wants to get inside the core, it has to pass one of the layers. Then it will find its way into the core as permeate. So it's a little bit complicated how it's all set up, but it does work. And so then we get the feed coming in the one side. Anything by the time we've crossed across this cylinder that did not make its way into that core area through those channels just leaves as the retentate. Okay, so spiral membranes, spiral wound, pretty interesting. Another way we can do it is tubular, and this is exactly like what we looked at. We just looked at one tubular membrane sitting in a chamber, but we could pack several in one chamber. Again, we just have to pipe the water to where it needs to go accordingly, right? So if we are adding, in this case, we're feeding water inside these tubes. We're going to filter through the tubes, and then it's going to be caught in this wider chamber. So we're going inside the tubes and then out. You can see a kind of expanded diagram here. Whatever does not make it through is just coming out the end over here, and that's going to be our retentate. Okay, so we've got these tubular, we've got the spiral wound, and I'll make a note here for these inside out, for these tubular membranes. There's a couple different ways we can actually operate them, and I think we've only looked at inside out so far. But if we imagine that we have a membrane that looks like this, we have a cylinder and it has some wall thickness, we could actually operate in one of two ways. We could go from the inside to the outside in terms of where the water can pass through the membrane. And if we're doing inside to out, that means that our separation layer, the actual membrane that's causing the separation, is going to be the inner portion of that tube, ideally. Because what we don't want is well, first of all, we don't want a very wide range of really small pores. What we want is a very thin edge where we have small pores, and the rest of the membrane is just a support. Bigger pores, it's just a support network. We don't want to have to force water through a long space of really tight pores. It's better if we can just shrink that to a very small, thin layer. So that separation layer for inside out should be on the inner side. Whereas if we operated outside in, then the water is going to be coming from the outside in some sort of direction and then leaving either way. From there, we'd have our concentrate, our feed, and then our retentate, or the permeate in this case. Now, in this scenario, the outer layer would be our separation layer. And I think we'll work on a problem next time, or maybe it's in the homework. But this difference here can actually make an important difference, because there is some thickness there. You can imagine there's a difference in surface area if you use the outer versus the inner. Okay, so not only operationally, we don't want particles getting stuck in there. So if we had a membrane that was designed for inside out, and then we started operating it outside in, it should be large pores up until that separation layer. And so if we separate these small particles after they've already made their way into the large pores, then they can't go further. That's going to clog up the entire support layer pore area. And that's not how we want to operate our membrane. That will get clogged in a really awkward manner. Okay, that'll make a little more sense in it. I think I've got a couple slides here in a moment on what that separation layer versus support layer kind of looks like. But I just wanted to highlight that these can be operated in either one if you're designed for it that way. There's one more membrane type that, or I guess a form that we would apply them in that's very similar I want to cover before we get into that stuff. And that would be hollow fiber membranes. And really all this is just lots and lots of small micro tubular membranes. Okay, so this is, instead of just having 4 or 5 in that chamber, we just make hundreds of millimeter size. And the nice thing, especially with the polymeric membranes, is that we can create these really tiny straws, essentially, with the membranes, with the membrane materials. So all other ways, this is going to work in the same manner. Again, you just have to do all the plumbing correctly to make sure that all of these membranes, you can flow water in from the inside of them, let's say, and let the water go from the inside to the outside, or you can potentially reverse that and have all the water sending into the inner spaces, right? You could conceive of reversing this flow, and you would have water meeting the outside of these tubes, collect all the water that's coming out from inside the tubes, and anything that didn't make it through the tubes is coming out as your concentrate. So you can operate them, all of the same things that applied here, how you can apply the water, how you can get the water, all of that, the direction of flow, inside out, outside in, all of that applies to hollow fiber membranes. These will all be the kind of the same principles. You just get a much higher surface area, right? So that's something we can notice here. A lot of membrane design is going to be about optimizing surface area, right? That was why I was showing and elaborating on that spiral wound, because you can get a lot more surface area that way. Well, you can get a lot of surface area doing this hollow fiber tubes. Really the one problem you might have would be that these are probably not able to handle quite as high pressure. If you design a larger tube, first of all, these guys are a little more likely you can make ceramics in that form, like in kind of a cylindrical form. Probably not these fibrous, like really tiny ones, and probably not the spiral wound kind of stuff. But the tubular ones, I've seen ceramic membranes that are kind of, a 1-inch tube or something like that. Okay, so that means for these, we do have some risk of collapse if too high pressure. There's also some maintenance concerns in terms of, okay, if something goes wrong and a fiber gets scratched somewhere in operation, maybe whatever particle removal stuff was happening upstream of this had some failure. Now we've got something in here that's just really too large for this to handle, and it physically scratches the membrane. Now you have a leaking membrane, one of the fibers or a couple of the fibers, and so that kind of compromises the entire membrane unit here. Well, how do you deal with that? How do you identify which fiber? Can we repair that? Or do you need an entirely new membrane cartridge system? So there are some challenges associated with it, but generally those are manageable enough that these are pretty commonly used. Okay, so I think next time it's going to be It'll be next time when I really get into the fouling, what that looks like with the separation layers and things like that. So it's a little ahead of myself. I've got a problem for us to work on, but before I do that, I want to get your feedback on scheduling an exam review day. So I'm going to start a Kahoot for you. So sign in with your 89 number. So have that as a record. It says there's a right answer. Don't worry about that. Just basically looking for, the homework is due on, I guess, did I make it the exam day or did I make it the day before? I think it's the class period before the exam, right? So Tuesday next week. I'm offering some cases. As you know, what I want from the homework is to see your effort to use it to learn, right? I'm offering a couple options to go over it before it's technically due. I'm going to leave that up to you if we do have a session before to use it to the best of your ability to learn. So I'm not going to go back and change the due date, so I don't think that would be kind. But I would suggest that if we do decide to have a review date first, that you probably ought to treat it as if it's due before, right? So that you get the most use out of it. You're not feeling like, oh yeah, I already know how to do this, and I just need to copy down the answers, right? So that's my impression. All right, anybody else need a moment? Okay. So we could do one potentially over the weekend, probably Sunday, or we could do Monday, Tuesday, or Wednesday. So those are the options. Probably in the evening. So I'm thinking probably Sunday afternoon or evening would be possible for me. Let me see. Tuesday I have 2 classes, so sometime 2 p.m. or later, or potentially in the evening. We can discuss in a moment in terms of if you have more specific feedback here. And Wednesday I could be kind of anytime in the afternoon, probably between 1 and 5. Okay, so a lot of people would prefer over the weekend, and I guess that would give you a little more time to study and reflect on it. Anybody have some major opposition to doing it on the early side? So Sundays. I will absolutely, yes, sorry, I should have said that. I will definitely, I'll do it live like we did that second lecture when I had COVID. I'll do it live, I'll record it and post a link. So what I'll probably do for these sessions is I will record it, I'll do it live, and so you'll be able to log in and ask me any questions. Maybe I ought to show you that here in a moment, but then I'll post a dedicated link. So if you have the link, which will be on the Moodle page, you can view it. I'll probably unlist it from my YouTube page, so you won't just find it scrolling through there, but you'll have the link in Moodle. Okay, so you can go back to it. Any of you ever? I mean, I guess most of you attended live that time. Did you have any issues commenting or sending questions? Should just be the comment box, and while I'm live, I'll see it in the next 5 or 10 seconds. So that way, it'll be a method for you to ask me questions. And on my end, this will be a little bit screen inception here, but I get the feedback right here, and I can open up a page myself to comment back to you text-wise if I wanted to. Oops. All right. Okay, so I will probably aim to
do that Sunday in the afternoon or evening. I'll let you know if I end up not able to do so, and if that's the case, I'll be sure to do it on Monday in order to match the preferences as best I can. All right, thank you. Any concerns about that? All right. Okay, so let's take a few minutes, look at this problem. You know, we haven't done any new math today, right? We didn't talk specifically about math any more than, hey, here's flux. We're talking about flux again. So I'm giving you a problem without having taught you any real new membrane related math. So this is actually just a word problem you could do without knowing anything about membranes, so long as you understood the context of, you know, the context of membranes. And so I'm hoping that this can help you see, okay, how am I thinking about the membranes, and does this make sense? Okay, so we have a membrane filter. It's used to concentrate an algae sample for culture analysis in a laboratory. A membrane with a pore size of 0.45 micrometers is used and rejects 90% of algae. I highlighted that because it might be worth looking at what happens if it was 100%, if it was 5%, you know, just as a practice, just to think, does your own intuition match what you would find when you solve it? So feel free to do that. Okay, so the filtration cell has a volume of 0.5 liter, can be operated either cross-flow or dead-end mode. Initially, the filter is operated in dead-end filtration mode. So if the initial concentration of algae is 3.5 times 10 to the 5th cells per liter, and the initial volume is 500 milliliters, what is the concentration of algae in the feed if 450 milliliters of solution is passed through the membrane? All right, so take a few minutes, work on that. I recommend starting with drawing it, and I'll join you in a few minutes, or we'll pick up here next time, but take a few minutes now. So seems like you've had a chance. You guys find answers that you think is reasonable? Maybe? Yeah, that's the thing, right? Did I read this right? Okay, so I started with a drawing here. And this, if you did have trouble, this might clear things up already. So it said we had a ½ liter volume, and we initially had a full ½ liter, right? 500 milliliters is ½ liter. And then we're wanting to know how much is left in the feed if we've passed 450 milliliters of the solution through the membrane. So we started with ½ liter, and we ended with, so I'm going to say 0.5 liters, and we have to subtract 0.45 liters from that to know how much we have remaining. So we have just 0.05 liters remaining, or that's 50 milliliters left in our system, and that's going to give us some answer to how many algae cells are there. Now, if we had 100% rejection here, this would actually be quite simple, because if all the algae were removed, then we could just take this ½ liter and notice that we concentrated it by a factor of 10. We went from 0.5 to 0.05. And so really, if we had perfect removal, this would just be 10 times more concentrated, because we had 10 times less water, but all the same cells. Okay, so we could write that out mathematically, but intuitively, we shouldn't be too far from 3.5 times 10 to the 6. Okay, but some of the cells are escaping, so we have to account for that. So let's write that out. So we had 0.45 liters filtered, and what we want to find really is the number of cells, the cell concentration. I'm going to say that as N. Let's say cells per liter is N, or N naught, or whatever. So we could say N naught, that's 3.5 times 10 to the 5th. Then we want to know N after, we want to know N remaining, right? So we could say the number that have escaped. Let's actually just get the raw number escaped. We'll say number escaped will be good to know, because then we can find the number remaining, right? All the others remain. We could get a raw number, and maybe we'll do that in a moment, that were there in the first place, which should just be half of this, right? So we could say, so that's cells per liter, and we had ½ liter. That's going to get us, what, 1.75, I think, times 10 to the 5th cells per liter, or cells total. Right? That's the total number of cells that we started with. So if we take the total number we started with and subtract how many escaped from that, we'll have the total number remaining, and we divide that by our volume remaining, and that'll give us our answer. So this number of cells escaped should be 10% times, that's 1 minus the 90, or 1 minus the 0.9. This should be 10% of the flow that left. So what we'll say is 0.45 liters times that 0.1. So that's our 10%. Times the initial concentration, that 3.5 times 10 to the 5th cells per liter. Okay, so then that 0.1, that'll just be 3.5 times 10 to the 4th times 0.45. I'm just going to get a calculator real quick. So 0.45 times let's say that's times 35000, so 35,000. So 15,750. Sorry. So if we check the units, we've gotten rid of the liters, and we're left with just cells. So we would do our 1.75 times 10 to the 5th minus 1.575 times 10 to the 4th. That's the number of cells, and divide all that by 0.05 liters would be our answer. Okay, does anybody have that number? I can get it real quick. So we'll pull this over here. 175. So that should give us 3.185 times 10 to the 6 cells per liter. All right, it looks like at least one of you feeling good about the answer. All right, does that make some sense? All right, okay, so we'll continue with membranes next time. And before then, I'll send you guys an email. So we'll probably have the exam review on Sunday, and if not, then on Monday. All right.